So we're working our way through intermolecular attractions, and we know that all these intermolecular attractions are opposites attract, okay? So the positives and the negatives are being attracted to each other, and the first three we looked at, it is somewhat obvious that there's going to be some electrostatic attraction because we have some positives and negatives. There's either a dipole in there or an ion in there, but we also introduced something called a dispersion force. Now we're going to, an induced dipole from something that was nonpolar, where we had to create polarity. We're ready to start with our next intermolecular force, which is called dispersion force. Somehow you can take something that is totally nonpolar and have it liquefy. So I have a molecule that's nonpolar, a molecule that's nonpolar. There's nothing there, it seems like, that would induce a dipole in order to have it become polar enough to be attracted and have opposites attract. But there is a way that this happens, and the thing that it's called is called dispersion force. Now, dispersion force is one name for it. Another name for it is London forces. So you'll see that in some of your readings. And for the long-winded ones, it is a London dispersion force. And for the really long-winded, which is actually a description, it is called an instantaneous dipole-induced dipole attraction. That's in parentheses. Nobody ever calls it that. They call it dispersion forces, London forces, or London dispersion forces. But all of our previous ones were descriptive, weren't they? We had ion dipole. We had dipole-dipole attraction. We had dipole or ion and induced dipole attraction. So all of them were descriptive, and now we've got a word instead of a description. So I've got for you a description of what it is. It's an instantaneous dipole, induced dipole attraction. So what in the heck is an instantaneous dipole? An instantaneous dipole takes into the fact that electrons are constantly in movement, all right? They're mobile, they're moving around, okay? Always moving. And overall, that molecule is not polar. We can't say that one end is positive and one end is negative. There are protons in there, there are electrons in there, but there isn't a positive and negative end. But in an instant, if you were to say freeze electrons, in that instant, those electrons might be in such a position that in that very instant in time, it is polar. So overall, with the constant movement of the electrons, it isn't polar. But in that instant, maybe it will be. Okay, so let's look at a picture. On the left is, let's say, a helium atom. So a helium atom is representing our non-polar guy. All right? It's non-polar. And so we've got our protons in the nucleus, and we have our electrons buzzing around. Okay? So here's one instant where the electrons are. Here's another instance where those electrons are. And let's see over here, let's make that one big. See if I can do that. I like it. Okay, over here is a third freeze frame where here's where the electrons are. Now if the electrons are here in this instant, can you see that the molecule, and I'm using that word molecule lightly, but in this instant this guy is polar. Here is the electrons on this side, and that's negative. Here is the nucleus with no electrons on this side, and that's positive. This is what we call an instantaneous dipole. At any instant, a molecule could be, that is not overall polar, could be polar. Now, if this little guy right here is in this instant polar, could he do all the same things a polar molecule can do? And that is, can it induce a dipole on its neighbor? And the answer is yes, it can. Okay? So that instantaneous dipole, so here it is, this instantaneous dipole is bumping up to instantaneous dipole. It's bumping up to a nonpolar molecule, and the electrons are shifting and saying, oh, there's a positive end, I'm attracted to that. They're shifting towards that, and they are inducing a dipole on this guy. So the instantaneous dipole is inducing a dipole on its neighbor. Now, as soon as that happens, the positive end of the one thing can be attracted to the negative end of the other thing, and we have this attractive force. It is called a dispersion force, or an instantaneous dipole-induced dipole attraction. That's its description. So this is what allows nonpolar things to actually liquefy. Without this happening, they could not get into the liquid state, and everything that was nonpolar would be in the gas state. But we know they liquefy, therefore, so here's kind of the order of logic. Number one, they do liquefy. You can get them into the liquid state. If that is true, the next thing we have to be able to say is there must be an intermolecular force, IMF, established, because that's what holds them together. If there is an intermolecular force, whoops, how did I do that? See if I can go back the other way. There. If there is an intermolecular force, then there must be a way to have electrostatic attractions. Logic says it has to happen, and this is how it's established. Okay, this is the way in which it happens. Otherwise, you would never have a liquid state with a nonpolar entity. So this dispersion force is what's going to allow all your nonpolar molecules to actually condense and get both into the liquid and the solid state. Now, what we know about this has to do with polarizability, all right? Dispersion force is going to increase and get stronger with molar mass. Now, why am I tagging in on molar mass? What we said was that polarizability increases with the number of electrons. As polarizability will go up as the number of electrons go up. Well, a quick and easy way to deal with the number of electrons is to look at the molar mass. It is always true that the bigger the molar mass, the more protons you have in the nucleus, the more neutrons, that sort of thing. But right along with it are more electrons. So we can do a quick and easy comparison of molar mass, which tells me a quick way of knowing about the electrons. I really don't think about the electrons anymore, but I know that as the molar mass increases, polarizability increases. It's easier to induce a dipole, therefore dispersion force goes up. So here are my representation of non-polar molecules, although they're atoms and not molecules. But these are things that can be non-polar, easy to see that they're non-polar. They can be liquefied. They can get into the liquid state. And we can make a quick comparison of their boiling points. Okay? The more strong the attraction between the molecules are, the higher the temperature is going to have to be to get it to get out of the liquid phase and into the gas phase. Okay? So this increased dispersion force is coming by molar masses going up, more ease of as we go down, we see a greater ease in polarizability. We see a greater dispersion force as we're going down. Okay? So as we go down, we have a higher molar mass. We have a greater polarizability because of it, and we have a greater, so we need an ER on there, we have a greater dispersion force. We can always see that greater dispersion force because it leads to greater melting points and boiling points. It takes a higher temperature to break the attraction. We'll write it down that way. It takes a higher temperature, which is more kinetic energy, to break the intermolecular force, the attraction between those molecules. Molar mass is not the whole story. We can't make a judgment about everything based solely upon molar mass. I have 3 different molecules here, and each one of these has the same molar mass, all right? Each one of these has 5 carbons and 12 hydrogens. So they are all nonpolar. They all have only dispersion force. And they all have the same molar mass, so we should think, well, they've got the same dispersion force. But look at their boiling points. They're completely different. So the question is, what is going on in this case? Well, let's think about these as Velcro, all right? The attraction between them is like Velcro. And I have a piece of Velcro on this guy and a piece of Velcro on this guy getting stuck together. And the strength of that stick together, it's the same kind of Velcro all the way across the way. But this molecule is much longer. And so it's got the same strength of Velcro, but it is a bigger piece of Velcro. It would take more energy to break that attraction apart, to pull these apart from each other, than it would take to break these apart from each other with the smaller piece of Velcro. So let's look at my hands and my arms as an example, okay? So I've got Velcro on my fists, and I attach them and I pull them apart. And there's a, I buy the exact same kind of Velcro and I put it on my arms and I stick my arms together, okay? It's going to take a lot less energy to pull my hands apart with that Velcro than if I stuck my arms completely together and I had to pull them apart, okay? So the strength of the Velcro is not different. It's the same loops and things that are holding it together, but it's over a much greater surface area of the molecule. And that is why sometimes, even though they have the same molar mass, and they're exactly the same nonpolar guys, but they have different shapes. And it's not very often that that will come into play, but if you look at two things and you know they have the same molar mass, they should have the same dispersion force, but they don't. It's evident they don't because their boiling points are not the same. Then you can scratch your head and say, why would that be? And generally it comes down to that. It comes down to the shapes of the molecules, and the greater the surface area of their touching, the greater the more energy it's going to take to break that attraction between them. All right, let's see what's next. I discussed that. So molar mass is the biggest part, all right? These aren't great big differences in boiling points here. So it's very, very rare that you have to go beyond molar mass to distinguish between entities here. Okay, so what do we know so far? Dispersion force doesn't just occur between nonpolar things. You can induce a dipole on something that's already polar. So you can take something that already is a dipole-dipole attraction, and because of being able to induce a dipole on a neighbor, and because of the fact the electrons are moving, we can say in this instant it's more polar than it was before, and it's going to induce a stronger dipole on this. So everything has dispersion force, whether or not it is a polar substance or a nonpolar substance. But the fact of the matter is this: if it is nonpolar, it is the only force it has. Okay, say that again. If it's nonpolar, dispersion is the only thing it has. But if it's polar, it still has this ability to have an induced dipole, instantaneous dipole-induced dipole attraction, this distortion causing increase in that. So what do polar molecules have? Well, they're going to have the dipole-dipole attraction. In addition to that, they will have the dispersion force. Now, if you've got polar molecules that are about the same size, they have about the same molar mass, two different molecules, and they weigh about the same, then they both have about the same dispersion force. But the polar one will have, in addition to the dispersion force, also a dipole-dipole attraction. So they're going to be more strongly held together. Now, a common misconception, and it's a misconception to the point that I've seen it in textbooks, okay? The common misconception is that polar molecules always, and I'm going to write it down and then we're going to cross it out because it's a misconception, always have stronger attractions, I don't know why I'm writing this sideways, than nonpolar. All right, so that is a common misconception. Polar molecules always have stronger attractions than nonpolar molecules. Now here's why it's a misconception. Nonpolar molecules only have dispersion force, where polar molecules have dispersion force and dipole-dipole. So that is if it's got both, surely it's stronger. but this is not the case. You can have some nonpolar molecules that are huge, very, very large nonpolar molecules that have grand dispersion forces, and it be a greater attraction than a wimpy little polar molecule. So this is a common misconception that you've got to get rid of. But we can always say this: if they are about the same size, okay, so we have two molecules that are about the same size, then they're going to have about the same dispersion force. And then you take on top of the dispersion force, add a dipole as well, then the polar molecule is going to be a stronger attraction than the nonpolar molecule. So we can say that with certainty. So there we go, the last statement there. If the molecules are not the same size, dispersion force tends to overshadow the dipole-dipole attraction, okay? It tends to play a bigger role in the attraction between molecules than the dipole-dipole attraction. So when you're comparing things and thinking about the magnitude of the dispersion force, look at the molar mass first and say, which one's bigger, okay? At least when you're just doing comparison between polar molecules and nonpolar molecules. So red exclamation points along that, because got to remember these things. You need to come back to this. You need to think through those statements, and you got to put those statements in your mind and have them make sense to you so that you can recall them. Here is a good image, and let's look at it on the screen a bit. That is comparing things that have about the same molar mass. So they have about the same molar mass, all in the 40 to 46 molar mass unit range, okay? We have this guy that has a dipole moment of 0.08. It's nearly nonpolar. Okay? It just has hydrocarbons. It is almost a zero dipole moment. So if it has a certain boiling point, which we can read off of here, that is caused by its intermolecular force. So we can kind of think about the height of this tower as not an increase in boiling point, but an increase in intermolecular force. It is going up as we go this way, just as the boiling point is going up. Those are tied hand in hand. So this first molecule, which is nearly nonpolar, I'm going to use a little red hashtags to say this much of it, don't know what that little guy is. Let's see if I can erase it. Yeah. This much of it is due to dispersion force. And maybe this little bit up here is because there's a tiny bit of polarity, just a tiny, okay? Now this guy has got a greater dipole-dipole attraction, okay? Because it's got a bigger dipole moment, okay? A greater dipole moment. But it's about the same mass, okay? So all of this is probably due to, and I'm trying to take this straight across from there, okay? All of this is probably due to the dispersion force, which is the same as this guy's dispersion force, because they're about the same mass. And so this little added to it up here is going to be caused by the fact that it's a little bit more polar. We've got all of this guy's dispersion force, and added to it, because this thing is a little bit more polar, we have this part, which is its dipole added to it. So the dispersion force generally plays a bigger role, okay? The dispersion force plays a bigger role typically than the added dipole-dipole attraction. So you could have two molecules. Bottom line is you could have two molecules, one that's really, really big and has a grand dispersion force, and it could have a higher boiling point than something that's small, because the dipole-dipole part is generally smaller than the effect of the dispersion force. Okay, so we have looked at our new intermolecular force called dispersion force, or London force, or London dispersion force, if you want to call it that. It is what holds a nonpolar molecule to a nonpolar molecule, and it is played out in everything. Everything has dispersion force, everything. It's just that if it's nonpolar, it's the only thing. And dispersion force if you're comparing two things that are about the same size, you're going to have about the same dispersion force. And then if they're different in their masses, different in their polarity, you would have dipole, dipole possibly added onto that. All right, so we've worked our way through, and I want to put my face over here where you can see me. Okay, we've worked our way through almost all, but not all, of our intermolecular forces. We started off by talking about dipole, dipole, dipole-induced dipole, ion dipole attractions. We've gone into this one, but there is one more. He's the granddaddy of all intermolecular forces that we'll cover next.